One of the most interesting areas of physics that I've explored is in the periodic motion of pendulums. I'm sure we all know what those are. Some mass on a string, swinging it back and forth. It turns out, for something as simple as this, there are quite a lot of cool properties that can come out of it, including a very nice demonstration for one of the most important conservation laws that govern our universe. Hello everyone, and welcome back to the C-Squared channel. Pendulums are really mesmerizing. They constantly swing back and forth seemingly forever. In fact, there's a whole area of classical physics for such motions like this, called simple harmonic motion. Even more interestingly, it also serves as a fantastic demonstration for the conservation of energy. But how does this all work? Well, let us consider a basic pendulum setup. We start by taking a long string of some length L, with an object of mass m being attached to the very bottom of it. We won't worry much about the dimensions of the object, so we'll consider this as something called a point mass, which is simply an object that has a mass but no volume. Now we're going to raise this mass up to one side with the string perfectly horizontal. This will be the maximum height of the pendulum. Now we let go, and what we see here is that the pendulum begins to swing from one extreme on the left side over to the other extreme on the right side, and it swings almost at the same height as what we started with. And of course, while this is swinging, the pendulum will always swing past through this middle point down here called the equilibrium position. Now, what is the equilibrium position? Well, this is the point where all the forces acting on the mass cancel out. So we have a net zero force. At any other position in this setup, you would have the combined effects of gravity and tension in the string, which will make the mass move towards the middle point. It's only at this central equilibrium position where the mass will remain still and balanced, because the tension forces in the string are equal and opposite of the gravity that's pulling it down. So when you release the mass from anywhere other than the equilibrium position, you'll see that it will constantly swing from side to side as it always approaches the middle point. And since the mass is trying to return to its original spot, there are forces at play to bring them back, and we call these simply restoring forces, which is, as I've said, is just a combination of gravity and tension. But how does this all link up to the conservation of energy? Well, simply put, the conservation of energy states that energy cannot be created or destroyed, it's just simply transferred from one state to another. In an ideal pendulum setup, so we are ignoring any outside effects and forces, energy is constantly interchanging between two different types. We have a kinetic energy and potential energy. So kinetic energy involves the movement of objects, so this would be, the energy in the mass as it swings from one side to the other. And potential energy is simply the energy stored in the object. So this would be seen at the points where the mass comes to a stop at either extreme of the pendulum setup. Now, in this ideal world, energy will never be lost in the system. So the mass will continuously switch between kinetic and potential energy. Therefore, what we can see from this is that at the points where the mass is at its maximum height, which is either on the left or on the right, we will see that this will have a maximum potential energy and zero kinetic energy. We say that because, well, clearly at the maximum point it's not moving. We can see that at either extreme the mass is not moving, so of course it needs to have all of its energy as potential energy. It's only when it begins to move, so when the mass begins to start swinging back, it begins to pick up speed, and so the kinetic energy begins to increase, and the potential energy begins to drop. When it passes through that equilibrium position down there in the middle, the mass loses all of its potential energy and has a maximum kinetic energy, because this is the point where the mass moves at its fastest. And of course after that, the mass will be going towards the other extreme now, and so it will begin to lose speed as potential energy picks up again, until it reaches the highest point. So this is over on the other extreme now. The mass comes to a complete stop again, the kinetic energy goes down to zero, and the potential energy is back up to a maximum yet again. And the cycle just continues as the pendulum swings back and forth between these extreme points forever and ever. Now you can visualize this out in quite a nice graph. Of course, you can see the kinetic energy and the potential energy curves are, different colored. And you can see how they interchange as the pendulum moves from one side to the other. So this is simply the conservation of energy at work, and that is because at any point during the cycle, the kinetic and potential energies of the mass are always interchanging with each other at the same rate. And to verify that this is a conservation, if you add up the potential and kinetic energies at any stage in the cycle, you'll see that the total energy you get should be constant throughout the entire thing. So for example, the total energy at one extreme will be exactly the same as the total energy as the mass passes through the equilibrium point. Let's say the total energy at maybe this point here would be exactly equal to the total energy at this point here, despite having different kinetic and potential energies. All it matters to keep this as a conservation law, both kinetic and potential energies have to be exactly the same at every point. That is nicely demonstrated for the ideal pendulum. Now, while this is very nice and simple in the ideal case, of course, this is not reality, because you can see the mass will eventually stop at the equilibrium spot after a bit of time, and that if you actually add the kinetic and potential energies together, that total energy will start to decrease over time as well. The reason for this is because, in reality, energy does get lost in the system. So as the mass swings from one side to the other of the pendulum, it experiences forces from air resistance, because the particles of air are constantly interacting with the mass, and this will slow the mass down just slightly. And if you keep it going for several oscillations, the pendulum will come to a complete stop, since energy is completely lost in the system because of air resistance. And this effect is called damping, and we don't see in just pendulums. Of course, that is the simplest example of such a thing, but we can have more exotic ones. For example, alternating current circuits in electronics. They actually experience simple harmonic motion as well. The electric current constantly changes from one direction to another, and in the UK, this typically has a frequency of about 50 Hz, meaning the current switches direction 50 times every second. Now, if we compare this with the pendulum, electronic circuits also suffer damping, but it's not because of air resistance, it's because of internal friction with moving electrons and the wire itself. And so energy eventually gets lost in the circuit in the form of heat. So that is the concept of simple harmonic motion, and how you can use this to demonstrate a really nice example of the conservation of energy in an ideal case. It also makes for some really cool mathematical analysis, or really awful depending on what you have to deal with, but at the end of the day, it really fascinates me with how much information you can get from conducting such a simple experiment. So thank you all so much for watching this video, and I'll see you all in the next one.